Okay, so one of the last sections we're going to do here is on U substitution involving rational and logarithmic functions. And there's three integrals we're going to take a look at here. And just like in that last video with the exponential functions, I'm going to adjust these slightly so that they follow more along the lines of the U substitution notation that we have. So this guy, right, would be the integral of u to the negative 1 du. Now, a lot of times you won't see it written like this. A lot of times you'll see it written as du over u, right? And so that integral is going to be the natural log of absolute value u plus c. And then, of course, this guy, right, so if we do the integral of ln u, then this would be u, right, u ln u minus 1 plus c. And the same thing here, right? We've got u and du, and so 1 over ln a of u, right? ln u minus 1 plus c. So again, we're just gonna go through a couple of examples here where we focus on identifying what u is, seeing if we can't figure out how to take these integrals. So if we just go through these real quickly, so here, u is going to be the thing in the denominator, right? So what's important to note is that when I do a problem like this, I want to make sure, like for example, if I had x minus 3, I want to make sure that that exponent right here is a 1. If that exponent is any other thing, if it's anything other than a 1, then we're not going to do this ln. We're going to use another method where we have like u to the negative 2. Okay, so you may want to go back and look at a few of the other videos on that if you're struggling there. But so with this first one, we're going to identify u as the denominator. Okay, the denominator. In this thing, right, if we're looking at the ln x one here, so for the integral of ln x, then u is just going to be what we're taking the natural log of, right? So u is, we'll call that the argument of the natural log. And the same thing down here, so u is going to be the same thing for this log. Just notice that ln and log are essentially the same function. It's just that the base is different. Here the base is a. For ln, the base is understood to be e, and that's one of those pre-cal topics that you probably have already encountered. So we'll jump in here and take a look at this guy, right? So we want the integral, or excuse me, if f prime of x is equal to 3 over x minus 10. Now this thing right here, that's a comma, all right? So if f prime of x is 3 over x minus 10, they want us to find the original function. In other words, it's just a fancy way of saying, hey, what is the antiderivative, right? So the integral of 3 over x minus 10 dx. Again, we talked about this a minute ago. U is going to be this x minus 10 thing, right? And then du is just going to be dx. So that gives us 3, right? 3 times the integral of du over u. We know this to be the natural log of absolute value u. So this is just 3 times the natural log of x minus 10 plus c. Fairly straightforward, right? It's just an indefinite integral. We're not plugging anything in, evaluating any boundaries or anything like that. In this problem, it may be a little hard to see exactly what's going on here first. So what I would do is I would look first to say, well, can I factor this thing on the bottom, right? Can I factor and simplify this integral? And it turns out that I can't simplify, okay? So the next thing I'm going to do is I'm going to just let u equal the thing on the bottom. And the reason I'm doing this is because I want you to see that when I take the derivative, I get a multiple of the numerator. So I'm going to take this 2, I'm going to factor this 2 out, and I have x plus 3 dx. So to get the x plus 3 dx by itself, I can divide both sides by u. Okay, so you may not have known to do that unless you've seen this worked out a couple of times. So essentially, x plus 3 dx is equal to du over 2, or 1/2 du. So in rewriting my integral, all of this, all that I'm circling in green, that is my 1/2 du, right? We'll refer to it over here. So that's my 1/2 du, and then the numerator, or the denominator, is just u. So if we simplify this a little bit, I'll pull the 1/2 out front, and I'm left with du over u, which we know to be ln u plus c. I'm going to make those substitutions back in, and I have 1/2 ln of absolute value x squared plus 6x plus 11 plus c. So this is a tricky one, and it really does do some good to see that worked out once. Okay, here's a little bit of a different type problem. So we're going to go and identify u here to be x squared, which makes du 2x dx, right? So we're gonna have the integral. Now notice I've got 2x dx in the problem, right? So 2x dx, you'll see that that's going to go away, and we're just going to have du. You'll see that x squared goes away. We're just going to have u in its place. And then we're going to apply that formula that we looked at on the first page. And so it's the integral of log base a of u du is going to be 1 over ln a. So in our problem, notice that a value is 3. 1 over ln 3, u ln u minus 1 plus c, right? So we're going to make our substitutions back for what u is. So I'll replace this u with x squared, right? So x squared over ln 3, ln of x squared minus 1 plus c. So now we get into some definite integrals, right? And we've already done the antiderivative of 3 over x plus 1. We saw in an earlier slide, that the integral of 3 over x plus 1 was just 3 ln u, right? And so earlier we went and we substituted back in for what u was equal to. But that's when we do the indefinite integral. When we do the definite integral, when we have those boundaries, remember we're going to leave the u in place and we're going to change these small numbers. Okay, so we're going to change the small numbers and figure out that if u is x plus 1, then that makes the upper boundary 7 plus 1, which is 8, and it makes the lower boundary 3 plus 1, which is 4. So if you're wondering, why am I plugging in 8 and 4? It's because we changed those boundaries. So we have 3 times the natural log of 8 minus the natural log of 4. So you may be wondering, how on earth do I simplify this? From pre-calculus, we talked about that when you subtracted natural logs, or subtracted logarithms in general, you could take their arguments and just divide those out. So 8 divided by 4 is 2, and that's where we're coming up with 3 times the natural log of 2. Okay, here we haven't done this integral yet, and so this will be a good one for us to look at together. I'm going to let u equal the thing that's being raised to the power. So that makes du dx over x. Recall that the derivative of natural log is du over u, or dx over x. So all of this, right, I'm going to circle this in green, all of that's going to be replaced by du, and ln x is going to be replaced by u. So if I rewrite my integral, it's u squared du. Now notice I have boundaries, so I'm going to rewrite those boundaries. So I've got to figure out, what does u equal when I plug e in for x right here, right? I'm going to plug e into x right there. So the natural log of e. Now, if you didn't know this, you can take your calculator and do this just as a little exercise in familiarity, right? So I'm going to figure out that e is 2.71, and I'm going to take the natural log of it. How about that? It's 1, right? But then I've got to take the natural log of 1 as well, right? I'm going to plug 1 into the natural log. If I take the natural log of 1, I get 0. So when x is e, I get a value of 1. And when x is 1, I get a value of 0. So my new boundaries, right, that's where the 1 and 0 come from. The integral of u squared is u to the third over 3. And I'm plugging in 1, so I get 1 to the third minus 0 to the third. I'm going to multiply that difference by 1/3. And my final answer is 1/3. Here's another problem very similar to the one that we just finished. And again, if you have some issues with this, please let me know. I'd be glad to work through this one for you, or any of the other Newton problems that you come across. I'd love to have your feedback. Please let me know what I can do to give you additional resources or help you through these in any other way.